Okay, let's dive right into this. Have you ever actually stopped to think about this classic physics scenario? I mean, we've all heard the story of the falling apple, right? But consider this for a second. If the Earth attracts an apple, causing it to fall, does the apple attract the Earth right back? Well, according to Newton's third law of motion, the answer is an absolute yes. The apple literally does pull on the Earth. Now, before you start looking for the ground to suddenly fly up and hit your fruit, we have to remember his second law, which tells us that acceleration is inversely proportional to mass. Because the Earth's mass is just so incredibly huge compared to a tiny little apple, the Earth's movement is practically zero. We just don't see it happen. But the pull? That pull is definitely there.
So welcome to today's explainer. Today, we're going to demystify the incredible, often invisible forces that dictate literally everything around us. From the massive celestial bodies floating out in deep space all the way down to the ground we're walking on, our physical world is locked in this constant, ongoing state of push and pull. I am so excited to guide you through these fundamental rules that structure our entire reality. Here's a quick look at our roadmap for today. We'll kick things off with the universal pull of gravity. Then examine free fall and acceleration, clear up the whole mass versus weight confusion, explore thrust, pressure, and area, and finally wrap up with buoyancy and Archimedes Principle. Let's get right to it. Starting with Section 1, Universal Pull of Gravity, how the universe pulls things together. It all really started with Isaac Newton sitting out there under a tree. But, his true genius wasn't just realizing that things fall down. Newton made this massive, brilliant leap of logic. He conjectured that the exact same force pulling that apple down to the grass is the very same force keeping the moon locked in its orbit around the Earth. He realized that the moon is basically always falling towards the Earth, but because of its incredibly high velocity, it essentially falls around it in a continuous circular path. The force keeping it in that circle, that centripetal force, is just the Earth's gravity. That one monumental realization breaks down into a single beautiful rule, the universal law of gravitation. Basically, it says every object in the universe attracts every other object. The force of this attraction depends on just two things. First is mass. If you multiply the masses of the two objects together, a larger product means a stronger pull. Second is distance. The force is inversely proportional to the square of the distance between their centers. To put that into perspective, it means if the distance gets bigger by a factor of 6, the force doesn't just get 6 times weaker, it becomes a massive 36 times weaker. It's also worth noting that the specific constant for this equation, known as big G, was painstakingly calculated much later by a scientist named Henry Cavendish using a highly sensitive balance. Moving on to Section 2, Free Fall and Acceleration, Gravity's Effect on Falling Objects. So the crucial takeaway here is this very specific number, 9.8 meters per second squared. When an object is dropped and falls toward the Earth under the influence of gravitational force alone, we call that free fall. And during free fall, the object's velocity is constantly changing. It's accelerating. By taking the mass and the radius of the Earth and plugging them into our gravitation formula, we get this constant acceleration for objects near the surface. We denote this local acceleration due to gravity with the lowercase g, which is totally different from that universal constant capital G we just talked about. And this brings us to one of the most wonderfully counterintuitive facts in all of physics. Acceleration during free fall is entirely independent of the object's mass. It sounds kind of crazy, right? But according to a very famous story, Galileo actually proved this by dropping differently sized objects straight off the Leaning Tower of Pisa. If you drop a crumpled up ball of paper and a heavy stone, they hit the ground at roughly the exact same time. Now, if a flat, uncrumpled sheet of paper falls slower, it is only because of air resistance, friction essentially pushing back up against it. If you were to suck all the air out of a giant glass tube, a light feather and a heavy stone would plummet and hit the bottom at the exact same instant. Let's hit Section 3, Mass versus Weight, clearing up a classic point of confusion. So let's really compare the two, because people mix this up all the time. Mass is simply the measure of an object's inertia, basically how much physical matter it actually contains. This is an absolute constant. Whether you're standing in your living room, floating in deep space, or walking around on Mars, your mass is exactly the same. Weight, on the other hand, weight is not matter. Weight is a force. It's the actual physical force with which gravity attracts your mass downwards. Because weight equals your mass multiplied by the local gravity, your weight absolutely changes depending on where you happen to be standing in the universe.
To really see how this plays out in our reality, let's compare the Earth and the Moon. The Earth's mass is astronomically larger than the Moon's, and the Earth is also much, much wider in radius. Because the Moon has significantly less mass and a smaller radius, it exerts a much weaker gravitational force on any object sitting on its surface.
If you actually do the math and compare those planet sizes, it works out perfectly to a fraction of exactly 1/6. The weight of an object on the Moon is exactly 1/6 of its weight on Earth. So if something weighs, say, 10 newtons here on Earth, it's going to weigh just 1.67 newtons on the Moon. Your mass doesn't change one single bit, but the celestial floor beneath you is pulling you down with just a fraction of the strength.
All right, Section 4, Thrust, Pressure, and Area. How the physical world pushes back.
To wrap our heads around this, consider this little puzzle. Why can a really heavy camel, weighing hundreds of kilograms, walk super easily on loose desert sand without sinking, while your bare feet would sink right in almost immediately? I mean, the camel is way heavier, meaning gravity is pulling it down with far more force, right? So why doesn't it sink?
Well, the secret lies in the relationship between force and area. When a force acts perpendicular to a surface, physics calls that thrust. In our camel example, the thrust is just the downward weight of the body, but the effect of that thrust completely depends on the area over which it's applied. We call this pressure. Pressure equals thrust divided by area. The unit for pressure, by the way, is called the Pascal, named after the scientist Blaise Pascal. A camel has these very wide, flat hooves, giving them a massive surface area. By dividing their heavy thrust by that huge area, the resulting pressure on the sand is actually quite low. Now, what's really fascinating is how this applies directly to you. Put yourself in that desert. If you stand straight upright, your entire body weight, your thrust, is concentrated onto the tiny surface area of just the soles of your feet. That creates super high pressure, and you sink deep into the sand. But if you were to lie down flat on that same sand, your weight hasn't changed at all. The thrust is identical. However, the contact area of your whole body is so much larger. The pressure is drastically reduced, and you don't sink. This exact same principle is why heavy army tanks use those wide, continuous chain tracks, and why a kitchen knife requires a tiny, sharply pointed edge to exert enough pressure to actually slice through a tomato. Which brings us to Section 5, Buoyancy and Archimedes Principle, Defying Gravity in Fluence. Try pushing an empty, sealed plastic water bottle underwater. You immediately feel this really strong upward push fighting back against your hands, right? Let it go, and it pops right back up to the surface. This upward force exerted by a fluid is known as upthrust, or buoyancy. Literally, any object immersed in a fluid experiences this force. It's a constant, invisible tug of war. Gravity is aggressively pulling the object downward, while the fluid is pushing it right back upward. So the million-dollar question is, who wins the tug of war? Well, it all comes down to density, which is just mass per unit volume. If you drop a piece of cork and a solid iron nail onto water, the cork bobs and floats, but the nail sinks immediately. Why? Because the cork's density is less than the water's. The upthrust from the water is greater than the cork's weight, so it pushes it up. The iron nail, however, has a much higher density than water. The downward pull of gravity easily overcomes the upthrust, and it sinks straight to the bottom. The core mechanics of this upward force were famously cracked by the brilliant ancient Greek scientist Archimedes. Legend actually has it that he was just stepping into his bathtub when he noticed the water level rising and overflowing as his body displaced it. He realized the direct connection between the displaced fluid and that upward force, and supposedly ran totally naked through the streets, shouting "Eureka!" which means "I have got it." He even used this very knowledge to determine the purity of gold in his king's crown. And this brilliantly illustrates what we now call Archimedes' Principle. It states that when a body is fully or partially immersed in a fluid, it experiences an upward force that is exactly equal to the weight of the fluid it displaces. This single, elegant principle is exactly why massive, incredibly heavy ships made of solid steel can effortlessly float on the ocean. Their wide shape displaces enough water to completely counteract their massive weight. It's also the core science used today in designing complex submarines, constructing lactometers to check the purity of milk, and using hydrometers to find liquid density. Which brings us to our final thought for this explainer. If gravity's pull is strong enough to bind the entire universe together, keeping the moon locked perfectly in its orbit, yet everyday forces like buoyancy and pressure can completely counteract it locally right here on Earth, how much of our daily physical experience is really just an invisible tug-of-war? Everywhere we go, from simply stepping onto the sand at the beach to going for a swim in the ocean, we are caught right in the middle of these perfectly balanced pushes and pulls. I really hope this explainer gave you a fun new lens to view the incredible physical mechanics of your world.